So first question number 3, week 7. Let's look at 7.11, 111. Steam enters a steady flow adiabatic turbine at 350 Celsius, 4 megapascals. Steam leaves the turbine at 120 kilopascals as a saturated vapor. Determine the isentropic efficiency of the turbine. Okay, so this is the new thing here. What is this guy? What are we talking about? Well, just like before, we had isovolumetric, which is the same volume, isobaric, which is the same pressure, and isentropic is the one that has the same entropy, right? Our entropy does not change. Okay, what does that mean? It means that we don't lose useful work or useful energy due to inefficiencies or to irreversibilities of our process. Okay, so let's go ahead into our page here. There you go. Okay, so let's talk a bit about that. What does that mean? Well, if I'm going from my one state here, I'm going down to a lower state of energy, like is the case with that turbine just there. I'm going to have a certain release of energy here due to this difference in state properties, right? This is going to be my work in my Q as we learned before, right? It has to be related to these two things according to the first law. But, okay, if my process is not isentropic, or in other words, if my process from here to here is not reversible, it's not a reversible process one that I can go back and forth, right? If it's not a reversible process, I'm actually losing some efficient energy, or useful energy, I should say, in this process, okay? So what we do is we have an imaginary problem that I'm going to state. I'm going to call 2s, s for entropy. And in this imaginary state, we're going from the same state 1 into this imaginary state where the entropy of this state equals the entropy of my first state. So I didn't lose any entropy. I didn't create any entropy. Shouldn't say lose. I didn't create any entropy during this process here. So in other words, this is the maximum work or heat that I can have out of this process that I can transform into useful work because I didn't lose any due to irreversibilities. Since we're on the subject, let me go ahead and talk about entropy. I think you probably learned this in the lecture, but just some quick things, okay? First thing, there's no such thing as conservation of entropy, okay? It's completely different from mass or energy, and don't ever think about that a concept of entropy having to be conserved from one to the other. That does not exist, okay? The entropy of one state and the other one, they're related to other things, and that's actually an inequality called Clausius Inequality, which states that the generated entropy of a process, of any process, has to be either 1 or greater than 0. Okay, so it has to be either equal to 0 or greater than 0, I should say. Either 0 or greater than 0. What do I mean? I mean that if we have a fully reversible process, which is this imaginary case here, my entropy generated will be 0. Okay, I haven't generated any entropy. I haven't increased the disorder of my universe. Okay, however, if I have a real case, right, an actual case, then I'm going to have reversibilities, and therefore I should have the increase in entropy. So I'll have the generation of entropy, and my entropy generated will be greater than 0. Okay, so another way to think of this is if we have a system, look at a given system here. Okay, inside the system, anything that happens inside this guy, it should have an increase in entropy. If by any chance I have a negative entropy, so if I have, let's say this change here from state 1 to state 2, I have a negative entropy, it means that I have to have either a positive entropy that accounts for that, compensates for that negative entropy on the surroundings, or an even greater entropy so that I have an increase on the entropy and I have a generation of entropy as we go. Okay, this is going to be clear as we go, hopefully. And you guys are welcome to stop me and ask things as we go. What does that mean in terms of the things that matter to us? Okay, so what is that isentropic efficiency? So the isentropic efficiency is a measurement of, as per usual, an efficiency is always how much we get out of a possibility, right? So it's a measurement of how much actual work I can get, how much actual useful work I can get, over how much I could possibly get on the isentropic system, okay? So think of it as an ideal system. If I do an ideal process here, going from 1 to 2 on this imaginary state, all with reversible processes, I would have a certain amount of energy. But since I'm going and I have some irreversibilities, right? Since I have some irreversibilities along the way, I'm going to lose part of that energy that was otherwise useful, and then I'm going to have a smaller energy output by the end of it. So this is my isentropic efficiency. Now, there's another way to think of this, because we know that if this is an adiabatic system, we know that this guy goes away, right? There's no Q whatsoever. So all the difference in work due to the energy difference from U1 to U2, plus, because this is a fluid, the delta PV term, all this difference is given in the form of work, right? So we can think of this guy, and since we know this is the entropy, we know that this is the difference in entropy. So this can be thought of as the entropy 1 minus the entropy of our actual state, so 2A for 2 actual, over the change in entropy if this were an ideal case, a completely reversible work being generated, okay? Last but not least, note that because of all the things that I'm telling you, this work here, let's call this guy, this W here, let's call it work rev for reversible work. So this guy will be greater than this guy here, right? The actual useful energy that I get if I have reversible work is greater than the one that I would get if I have irreversibilities in my process. So this defines our isentropic efficiency. It's also known as our second law efficiency because it's related to the same principles, okay? And one thing that's very important to note is if we have a compressor, so C for compressor instead of turbine, this is all flipped, right? Because what happens if we have a compressor? Then our situation is the inverse, right? Then we have a lower state of energy, and we are aiming to go to a higher state of energy here. So therefore, I need to give energy to my system, right? I need to put work into this system to be able to go to escalate upwards, okay? Now, if I have a system that's completely reversible, I have to put less work than I would have to put otherwise if I have the reversibilities and I'm losing that energy due to inversibilities, right? So in the case of a compressor, it will be the other way around, right? The isentropic will be here on top, whilst the actual work will be here on the bottom, because I would expect the actual work to be greater than the isentropic one. And if I can make it be exactly the same as isentropic, it means I have to put the least amount of energy as possible into this system. Okay, so obviously this guy is going to be flipped as well, and I'm going to have the 2s over here minus the 1, and over here I'm going to have the 2a minus h1. Okay, this is the case for a compressor and an adiabatic transformation. Okay, so that's our starting point. This is where this is the things we need to know so that we can jump into this problem. Right, so let's see what we have. We have a turbine. We have two defined states. Let's put them down. I have my turbine there. This turbine is operating with steam. And then we have 4 megapascals on this side here and 350 Celsius on this side here. And then on this side, I have 120 kilopascals, and it's a saturated vapor. So I have the two states are completely defined. What am I after? I'm after the isentropic efficiency. So what do I need? I need the entropy for state 1, the entropy for my actual state 2, and the entropy for my states, my imaginary state 2s. 1 is completely defined, 2 is completely defined. What we don't know is this guy here. That's what we're going to go after in this problem. Okay, so then we can plug it in and finish this off. So let me start by writing down what we do know. And what we do know is we look on our tables. Okay, look on our tables. You're going to see this is superheated. I'm not going to go through those steps because we did this over and over again. Or you go to the saturated one, you see that your temperature is greater than your T-set, or your pressure is smaller than your T-set. So it's superheated. So I can go to A6, and I'll go on page 910. And I'll grab my enthalpy 1 from the table, and I'm also going to grab my entropy 1. This is the new thing here, right? This is 3093.3 joules per Kelvin. And this guy here is 6.5843 kilojoules per Kelvin per kilogram. And there's also a Kelvin here, right? So it's per kilogram and per Kelvin. I'm putting it in red so that you guys don't forget, because students like to forget. Okay? So, why did I grab the entropy? Well, if this state here, the imaginary one that we're thinking about, is a state with completely reversible process, it means that we didn't create any entropy, right? So the entropy, the disorder in this state here, is the same as the disorder in that state there. So if I know the entropy for this first state, it means that I can also say that this is going to be the same entropy for this state, just like it's said here, right? That's why I'm grabbing my entropy for that state there. And then for my other state, my state 2, actual state 2, it's a saturated vapor, so I'm going to go ahead on page 5, on table A5, page 906, and I'm going to grab the enthalpy 2, which will be our saturated vapor enthalpy. However, and this is the dull part of this specific problem, we don't have on the table anything for 120, so we're going to have to interpolate. Okay, so let's interpolate quickly. My P that I have on the table is 101,325, and I also have for 125. And I'm looking for 120. In my saturated vapor one, I have 2675.6, and I have 2684.9. Okay, so I can interpolate for the 120. And I got, what did I get? 2682.9. That is kilojoules per kilogram. Okay? Give me 1 second. All right. So we now have the enthalpy for our second state, 2682.9 kilojoules per kilogram. Okay, so now check it out. We have almost everything we need. Okay, we have this guy here. We have the actual second state enthalpy, and we have the first enthalpy. The only thing we don't know to be able to calculate the efficiency is this imaginary enthalpy here. So that's what we need to go after. To go after that imaginary state, define that state to be able to find everything that we need. I got a question here. Sure. Okay. Oops. Sorry, Jackson. It's supposed to be to Sure. Okay. So far, so good, guys. So I'm just answering some questions that I'm getting on the chat. Let's make sure that this is showing up. Okay, so this guy is this guy here. So just send it up there after the interpolation. Awesome. So now let's define this second state here. We need to find properties for it. We need to find two things to define our state as per usual, right? So let's cross this guy out here. And I'm going to go ahead and do it. Let's write what we're trying to find, efficiency of the turbine. And we need H1 minus H2A over H1 minus H2S. Okay, and we already have most of the data, right? We have 3093.3. We have 2682.2. Then 3093.3. And then we're missing this one guy here, that we're after now, trying to find, so that we can plug that guy in and find our efficiency. Okay, so our efficiency is gonna, so we can define our efficiency. So let's define that guy. What do we know about this imaginary state? We know two things. Okay, the first thing that I know, let's call it state 2s. Okay, again, S for entropy. Where's my limit? Okay, this is my limit. Okay, 2s for entropy. So what do we know about this state 2s? Well, we know two things. We know that the pressure on this guy is the same pressure as my actual state, because we know it finishes off at this pressure here, which is 120. And I also know that the entropy of this state, 2s, has to be equal to entropy on state 1. Okay, so I know my entropy and my pressure. My entropy is 6.5, and my pressure is 120. As long as I have two state properties, I have to define state, right? That's the same thing as it's always been. So what are we going to do? Let's go ahead and jump into our table, property table. And let's have a look. We're looking for 120, and we know that that's not on the table, but we do have 125. So let's use 125 as a guide, and from there we can work our way for 120. Okay, entropy, this is the last column here, entropy. Okay, so let me highlight that for us. Entropy there. Okay, if this were saturated vapor, our entropy would be 7.2. If it were a liquid, it would be 1.37. Our entropy in our imaginary state is 6.5. So what does that tell us? Our imaginary state is therefore a
saturated mixture.
That's correct. Thank you very much. Okay, so we can write that down properly, and we can go ahead and write these values down, because we're going to be, oh, don't worry about these. We're going to be using it, but we have to interpolate for 120. Okay, so how do we write this? Well, because my S liquid is smaller than my actual S, or 2S, and it's smaller than my vapor, then this guy is a mixture, right? It's a saturated mixture. And now comes the dull part of the problem, that I'm going to have to interpolate heaps. So to be able to find the quality, as per usual, all we need is to put the whatever property we have and subtract by the liquid one and the vapor minus the liquid. Okay, you guys learned already. I showed you that one column in the middle, that FG, is the same thing as this difference here. So you can use that, or you can just grab vapor. It's up to you. I'll use FG just to keep you guys on your toes, so make sure you are on top of what we're doing. Okay, so let's go ahead and interpolate, because we don't know the vapor one, we don't know the liquid one, because we only have values for 125 and we want for 120. So what are we going to do? Let's do interpolation here. Pressure, again, same thing. 101, 325, 125. We want the pressure for 120. And what are we looking for? We're looking for S of liquid. Also looking for SFG. And I'm also going to be looking for the enthalpy, right? Because if we know that check it out, if we know already it's a mixture, we know the enthalpy of this state, enthalpy 2S, which is what we're looking for, is going to be a combination of the enthalpy of the vapor times X plus the enthalpy of the liquid times 1 minus X. Yeah, we know that already. So we can go ahead and grab the enthalpy for the liquid. Pablo, don't you need the enthalpy for the vapor? I do, but I have it already. We already did that interpolation back here, right? We did interpolation for 120, and we got the vapor, the saturated vapor already. So I only need these three guys. Okay, let me share with you what I have. 1.3069, 1.3741, 6.0476, 5.91, 419.06, 444.36. Okay, I'm going to interpolate these guys using these values for 120, and I got 1.36, 5.93, 939 and 439. Okay, those are the values that I got. And then with these values, we can go ahead and solve this guy here. Okay, so this is going to be 6.58 minus 1.36 divided by 5.939. What did this render? This renders 87.97%. Okay, so way more vapor than liquid. Let's just think for a moment to see if that makes sense. Well, when we were looking at the other process, at the actual process, we were going from a superheated one to a saturated vapor one. Okay, now we know we should expect this state to be lower in energy because we actually can extract more out of it. Right, so therefore, I would expect my guy to be further down the dome, and that would be more liquid. This had 0 liquid, this has about 15% liquid. So that makes sense. Okay, likewise, what needs to make sense is that our entropy for this state needs to be way closer to this guy here than to this guy here, right? Because we have way more vapor than we have liquid. Don't forget that as you're doing, because a lot of you guys do, and you just do your mistakes because of these silly things, right? 2s, so that will be 2682.9 times my 87.97% plus, I'm not going to have space for this, so I'll just do it over here on this side here, so you're not struggling to see. Okay, so just solve this equation over here. So 2s, it's going to be 2682.9, which is the value that we had before, times my 87.97% plus my liquid one, 439 times 100% minus 87.97%. Right, so my H2S ends up being, what do I have here? 2413. This number has to be smaller than the actual one, and indeed it is. It's 2600 versus 2400. So it makes sense. And that's the value that we were missing, right? So with this value, we can go ahead and plug it in here. 2413. Solve this math. And this guy is 0.6326, and it goes on. So we can approximate this to 60.3%. What are our conclusions from this problem? Okay, our conclusions are, well, there are irreversibilities during this process, and they account for about 40% of what we could actually transform into useful energy. So we lose, okay, we don't destroy energy, that cannot happen because of the first law, right? But we stop the useful energy from being 100%, and we go down to 60%. So instead of having our difference here, so this amount of work, 3,000 minus 2,400, about 6,000 kilojoules per kilogram, we're only going to be able to grab this difference here, which is about 400 kilojoules per kilogram, right? So this 40% that we're losing is due to the irreversibilities of the process. And this is very important for you guys as engineers because this is where you have leg room to work, right? This is where you can improve your process. Because you can't create more energy from nothing, that's impossible, but you can definitely make a process that is closer to your isentropic process, so you can make this guy more efficient and therefore have a better process. That's the whole idea around looking for the second law efficiencies and isentropic efficiencies.